me, okay, so we are recording this session and it will be shared in the website of EuroWisdom. And let me say a few things about EuroWisdom Forum. We aim to provide a platform to support, empower, and encourage the participation of all genders in operational research within the Euro organization. You can find the Euro EDI policy on the Euro website, actually. And so we have a program called Young Women for OR. So every year we select, according to their achievements, young professionals, academicians throughout Europe, and we select 12 of them. And this is the cohort for this year. And today's presenters are Carolina, Lorena, and Georgia. And we have an expert speaker as well, Dr. Zümbül Atan. She's an associate professor at the Industrial Engineering and Innovation Sciences Department of Eindhoven University of Technology. Her main expertise is on supply chain management and also on revenue management and retail operations. She serves as the research director of the European Supply Chain Forum's FMCG community. So first we will have 3 talks by Carolina, Lorena, and Georgia. And after that, Zümbül will give her comments. Then we will take your questions. And at the end, we will have some time for chatting, for socializing. So I also want to remind you that we hold these webinars throughout the year. So there will be another one in November on city logistics and mobility. And we will have a winter event to wrap up the year in December. We also have a research program. We have a white paper promoting gender equality and inclusivity in Euro activities. And we have another research topic in progress. It's about co-authorship networks in OR by survey and interviews. So please keep in touch with us. Here you can see our website and email, and you can join us on LinkedIn and get our announcements. So, okay, let's start with Carolina then. Let me stop sharing.
Can I share?
Sure.
Okay, I hope you can see it. Right.
Yes, we can.
Yes.
Okay, so good morning, everyone. I'm Carolina Morais. I come from Instituto Superior Técnico in Lisbon. And today we present the work I developed together with Professors Tânia Ramos, Daniele Vigo, and Ana Paula Barbosa Pova. This work is entitled A Two-Phase Methodology to Solve a Sensor Placement Problem in Waste Management, based on a vehicle routing problem with Detours. I will start doing a briefly introduction, then I will describe the problem and the methodology we developed to solve it. I will show you the cases that we use it to solve this problem, the results, the cost-benefit analysis, and some conclusions and future work. I must start to say that the amount of municipal solid waste is highly variable, and so it's very difficult to forecast its accumulation. This is, how can I say, it's characterized by high uncertainty, which is associated, so that the waste management operations are often related to high inefficiency, which is translated in high transportation costs and pollutant emissions. Usually a blind collection is performed, where static routes are usually performed to visit all waste bins, regardless of their fuel levels. Opposite to this, we can perform a smart collection, where volumetric sensors are used to transmit real-time information on waste bin fuel levels, so that we can reduce uncertainty and increase the collection operations efficiency. This can, however, be expensive for waste collection companies that needs to sensorize all containers. We saw study how to select a sample of strategic containers to monitor so that we can optimize routes using real-time information. Here we have to tackle two different decisions. A first one, which is a tactical decision, which is which container should have a sensor, and an operational decision, which is how to design the optimized collection routes to perform using real-time information. We here work on the idea that while some containers have a more regular collection frequency and must be visited in a more regular way, other containers have a more unpredictable behavior and should therefore be sensorized. We call the regular containers, the containers which require regular collection, regular containers, and the more unpredictable one, non-regular containers. We use the idea that any days when planning a route to visit the regular containers, we can plan which non-regular to visit based on real-time information transmitted by sensors. In this way, if it's necessary, the non-regular containers can be visited through a detour made from the regular route. We also consider that when a detour is performed, it can be worth to collect a group of similar containers which are located nearby, so that we only install one sensor per non-regular cluster. To solve this problem, we developed a two-phase methodology where first we solve the tactical decision and then we solve the operational decision. Basically, in the first phase, we use a clustering algorithm to cluster homogeneous containers into clusters. Then we classify those clusters as regular or non-regular, depending on the collection frequency. And we finally sensorize, we select the most representative container within each non-regular cluster to sensorize, to receive a sensor. Then in the second phase, we solve a shortest Hamiltonian path problem to decide the interpath to be traveled within each non-regular cluster. And then each n days, we solve a clustered vehicle route problem with profits and detours to design dynamic routes that regularly visit the regular containers and the selected non-regular containers. In the first phase, here we just give you some detail about each phase. I'll be briefly, and then in the end you can say bring me questions if you have any doubts. The first step is the clustering algorithm. We first define the criterion and some importance for depending. That's because depending on some weights assigned to this criterion, we can define different scenarios. We, for example, define a higher coordinates importance scenario, a neutral scenario where we give same importance for coordinates and average filling rates, and a higher filling rates importance scenario. Then we use a hierarchical agglomerative clustering algorithm to obtain baseline clusters. And then we try to merge those baseline clusters so that we can have a lower number of clusters. We define a maximum radius limit and a minimum compatibility threshold. We merge pairs of baseline clusters which are within the defined radius and for which compatibility is higher than the threshold. Then in the second step, we define an average filling rate for each cluster and classify then according to this average filling rate as regular or non-regular clusters. We then select a container within each non-regular cluster to be sensorized, and depending on the risk tolerance, we can consider two different cases: a risk averse, where we select the container which has the highest average filling rate, and a risk-seeking approach, where we select the container which has the lowest average filling rate. Then in phase 2, we first solve the shortest Hamiltonian path problem so that for each non-regular cluster, we can obtain entry and exit nodes, optimum sequence to visit the intra-cluster nodes, and the intra-cluster route distance. Then every any days, we solve the clustered vehicle routing problem with Detours. After receiving sensor information, the real-time information for the sensorized container fuel levels, we estimate the fuel levels for the non-sensorized containers and calculate the must-go non-regular clusters. I mean, the non-regular clusters which must be visited to avoid overflows. We then solve the cluster vehicle routing problem with Detours to decide which detours to perform, how many routes to operate, and how is the optimal visiting sequence for each route. The clustered vehicle routing problem with Detours maximizes profit, which is defined as the difference between revenues from selling collected recyclable waste and traveling costs. And the specificity here is that if a non-regular cluster is visited, a single edge is traversed, which is the entry node and the exit node of the cluster. We then use a case study to solve this problem. It's a case study from a Portuguese company responsible for recyclable waste collection in Portugal. We use a case for paper cardboard. 2 different static routes are performed periodically. They have a depot and 98 containers. And we had access to data from April to July 2018. We defined a training period. We had access to the collection team records. We then calculated the average number of days between collections, which is equal to almost 7 days. Then we calculated, to calculate the amount of waste, we relied on the average of intervals recorded by collection teams. And then for each container, we computed a filling rate and the standard deviation. We then defined a testing period of 12 weeks and simulated new data on containers fuel levels using a uniform distribution. This is the scenarios tree we obtained, varying different configurations within the first phase of the 2-phase solution approach. And by solving the first phase, we can see that a different number of non-regular containers are obtained. This different number of non-regular containers also represents a different number of sensors being installed. I mean, if you have 27 non-regular clusters, you have 27 sensors installed in this case. This is just an example. As you can see, the baseline clusters, the final merged clusters, the non-remote containers in red, and the sensorized containers in a black dot. Then in phase 2, solving phase 2, we can see that a risk-seeking approach gives us higher profits, which was already expected, usually for a higher radius for merging, we have a lower number of sensors and a lower profit. We can state that the profit increases when we have more sensors. Just very quickly, we did also cost-benefit analysis. We analyzed 2 additional scenarios. We solved the cluster vehicle routing problem to minimize total distance in a scenario where no sensors are considered, and then a scenario where sensors are considered to be installed in all containers, and we solve a vehicle routing problem with profits to maximize total profit only when it's necessary. We calculated the difference between profits and estimated the value of perfect information for the sensor. Comparing the value of perfect information, we can see that the other scenarios, the scenarios where we have sensors in not all containers, result in higher profits, usually result in higher profits than the scenario where we have sensors installed in all containers. Usually when we have 20% of the containers sensorized, to have lower estimated value of perfect information, and the peak is registered when we have around 25% of the sensors of the containers sensorized. Just to conclude, we see that a more profitable collection depends not only on how many sensors are installed, but also on where they are located. When clustering containers, it's more profitable to consider a neutral scenario. We rely on more homogeneous clusters, and a risk-seeking approach usually results in higher total profit, but overflows may occur. We are working on testing, first classifying, then clustering. We also are working on using standard deviation as additional criteria in clustering, and we are also working on consider uncertainty and estimated field levels of monitored containers. Thank you very much, and sorry for the 2 minutes more.
Thank you, Carolina, for this interesting talk. So we'll proceed with Lorena next.
Hi, can you see my screen?
Yes.
Yes.
Excellent, thank you. So let's see if come on, doesn't allow me now. Oh God, one second. Now it's full or?
It's not full yet. Now we are not sharing. You are not
Something
sharing.
is happening there.
It's okay now.
Now? Excellent. Okay. So hi everyone, my name is Lorena Reyes. I am happy to be here and share with you my research project. So I belong to the Dr University Magdeburg, and I am interested to deal with disrupted road network in a post-disaster phase. So I work together with Jana Boll and Professor Patrick Hirsch from University of Natural Science, Natural Resource and Life Science in Vienna. So this is the structure of my presentation. I will skip that slide and start directly with the motivation. So we are interested to study rural areas and mainly disrupted road network because in a normal state, the road accessibility of a rural area is quite poor. And when a disaster occurs, but it's getting more complicated because some roads disappear because they are damaged or blocked with some debris, as you can see here in the picture. So when the disaster occurs, the first thing that the humanitarian aid organization are doing is delivery a team which are the responsible to extract the information and collect or giving the information which kind of roads are working after the disaster occurred. So our proposal here is that we can use an unmanned aerial vehicle, drone or UAV. So from now I will talk about UAV to perform that operation. And in that way, we can make more efficient that operation, reduce the risk for humanitarian aid workers, and try to save labor in that operation. So before moving to the main topic of our project, the main idea of our project, I want to show you some findings in the literature. So that is a big summary of the literature. We figured out that there are few papers related to immediate response operation and disrupted road network. And mainly of the findings are focused on disruption on nodes, few related to disruption of edges, that is quite related to our topic, and a combination of those disruption are few papers considering that. So the main characteristic here is that some authors are considering deterministic scenarios for a post-disaster stage, and others are aware of the uncertainty component in a post-disaster stage. And the way that they are dealing with that uncertainty is based on a stochastic approach, mainly scenario-based methodologies. And that means that what we discover here is that there is no proper tool that allow me to make online decision or decision in real time based on partial information that I get when I am exploring the aerial network. So now that is the academic findings from the literature review, and here from the practical perspective, so that is no new idea, using UAV for humanitarian operation. So there are some institutes and humanitarian organizations that are including that technology into humanitarian operation. And what they are doing here is defining what they call a passive routing. They define a zigzag routing, as you can see here in the picture, and they are collecting these videos or pictures, put together like a puzzle, and estimate what is the state of the road. So here, what they complain is that information is inaccurate, and because the driving range limitation, they are not able to explore the completely affected area. And also there are some part of the affected area that are explored and are completely unnecessary. So then thinking on that problem, so our project is motivated on that, and we characterize that problem as a unmanned aerial vehicle routing problem, considering that our routing decision involved two road network, one the road network and the other one is the aerial network. And the main challenge here is, as here is in my research question, is how I can reach my victim's location from the DMC after the disaster occurs. So that means that I need to detect which roads are working after the disaster occurred. And here with victim's location, I am referring to village or a small community here because we are talking about rural areas. So that is the challenge. So detect which kind of, which roads are working within the minimum time. So I will give quickly an example of what is happening here. So assume that we explore this, the bottom part of the network, we detect here a disruption. And from that part, we report the disruption and we need to redirect the route of the UAV in order to recap the routing. So what we learned so far is that that route is working. So here is the third network is the output of our algorithm. So that is the route that is working. So now assume that we continue our exploration, we detect another disruption, report the disruption, and again, we need to redirect the UAV. What we learned so far, here is nothing because we don't discover a new path that is working. But if we continue the exploration, we can detect that the top part of my network is working. And that is what we are expecting as an output of our algorithm, the collection of functional road that is working after a disaster. Here, the key point or the challenging point is that we just have the information about the state of the road in a pre-disaster situation, but we don't know the state of the road after the disaster occurred. So that is the tricky part here. So that means that we need to define a rule to prioritize the road, in which order I should explore the road. Then what happens if I discover a disruption, how I can redirect the UAV, and then check the driving range limitation. So going back to the how I can prioritize the exploration of the road. So we define what we call a labeled network, but we compute a labeled network after performing a cutting procedure, which is removing all part of the network which are completely unnecessary to avoid unnecessary exploration. And we define 3 different criteria to prioritize those roads. So one is the classical one, which is the distance. The second one is the connectivity, which we are trying to cut the structure of the network. And the last one is the combination of both criteria. So that is how we define the priority for exploring the roads. So as soon as we have that priorities, we start thinking on how we can deal with disruption, and we propose 2 strategies. The first one is the jumping strategy, that assuming here that we already explored the green part, we are here and discover a disruption. So what we are doing is scan the labeled network and detect which road is the one with highest priority and fly to that road and explore that road. The second approach is similar, but I am trying to reconnect immediately my path to the network that I discovered so far. So that is the difference between the two strategies. One is more conservative compared to the other one. Now, thinking of the driving range limitation, so we define a basic strategy, which is considering a dynamic buffer. Depending on the location of the UAV in my road network, I need to be able always to return back to the DMC, the Disaster Management Center, to perform a refueling operation. So that means here that we are assuming just the DMC as a refueling station. Just to be more safe and avoid any failure road, we consider 2 extra strategies. So one is the extreme conservative, that each time that I am passing by the DMC, I decide to perform a refueling operation. And the last one, which is a moderate conservative strategy. So each time that I am passing by the DMC and my tank is 50%, I decide to perform a refueling operation. So that is the brief idea of our algorithm. So here I want to explain you about the computational experiment. We play with the 3 criteria to prioritize our road network. We play with the 2 strategies to deal with the disrupted road network, and the 3 different strategies for the driving range limitation. To have a more interesting results, we simulate 3 different scenarios. low disruption level, which means that 30% of my ROAD is disrupted, medium and high, 7 instances with up to 100 nodes. And the seed was the one that allowed me to generate different disaster per disruption level. So here regarding the experiment, what we did here was we compare both strategy, back and forward and jumping strategy. We compare the 3 criteria, but here, because of time, I don't explain that we define a general equation that we define an alpha value. When alpha is equal to 0, we are defining the priority based on the connectivity. When alpha is equal to 1, we are defining the priority based on the distance. And something in the middle is the weight criterion. And what you can see here is the gap between, the gap over all instances between the best road, which means the one with the minimum time, and the one that you get from considering each of those priority or one of all of those criteria. So here is the performance for each of disruption levels that we consider. And that means that the values here close to 0 are the best exploration strategy. So it's evident that we can improve. And what is evident also here is that the jumping strategy doesn't provide a good performance, and the best one is the back and forward, and considering a combination of both criteria. So regarding the refueling strategies, what we are trying to do here is count the frequency, try to count which is the best refueling strategy in the number of time that I get the best exploration road, considering that the refueling strategy. And the winner strategy is the moderate conservative strategy, because the time that I need to spend for each refueling operation. So now for close my presentation, so the algorithm is quite fast. There are a lot of improvements that we can do there, but it's solving instances with 100 nodes in almost 1 minute. And then we provide some managerial insights. So we say that the best exploration strategy is the back and forward, and you need to consider both criteria, distance and the connectivity. And the best refueling strategy depend on the disruption level of my road network. And we have a lot of research questions, but I just put here 2 points. The one is that the idea of the labeled network can help me to discover or to define what is the order to recover those roads in order to improve the accessibility of the affected area. And the last one is we can plan periodical exploration in order to catch the changes in my disrupted road network. So that is my presentation. Thank you so much for your attention, and I will be happy at the end to answer your question and or receive your comments.
Thank you, Lorena. Thanks for this excellent presentation. And Georgia will be next.
Okay. Can you see my screen?
Yes.
Okay. So, good morning to everyone. I'm Georgia Fargetta, and this work is in cooperation with Professor Laura Scrimmali from the Department of Mathematics and Computer Science of the University of Catania, Italy. And the title of my presentation is A Dynamic Equilibrium Model of the Closed-Loop Supply Chain Network Equilibrium for Second-Hand Collectibles. So first of all, I want to present the problem. So today I present a sustainable closed loop supply chain network in which we consider some collectibles items in a time-dependent framework. We consider in our CLC network multiple manufacturers, multiple retailers, multiple demand market in which the consumer purchase the new product and collect them. So collectors distribute the used goods through an online platform, and for an online platform, we consider eBay for this platform. And the criteria of each player in the network is the total profit maximization. This is the outline of my talk. So first of all, I present my motivation to start this work, this research. Then I present briefly the CLC network. So the optimal behavior of the manufacturers for the retailers, of the consumers in the forward and in the reverse logistics. And finally, I present the behavior of the online platform, and considering some numerical example in which we consider the equilibrium condition of the CLC network. So the motivation starts from my experience because I'm a collector, and during April 2021, I saw that a particular card called Black Lotus is on eBay a lot of amount of money, and it's purchased before this screen of images by Dario Moccia for 38,000 euros. And for this card, there are 1,100 copies of this card in the world. So the CLC network that we consider the manufacturers from 1 to M, the retailers from 1 to R, the consumers from 1 to K, and finally the online platform. The dashed lines represent the backward supply chain network. The optimal behavior manufacturer is characterized by this function. The aim is to maximize the data about this function, and these are the constraints that we consider. For example, the non-negative of the quantities that a manufacturer send to retailers. These are the some costs that we consider. For example, the production cost, the transaction cost. Also, we consider the production capacity. Also, and all variables depend on time. Here we can find the maximization of our function that we consider for the optimal behavior of retailers. We can, for example, consider the transportation cost from hem for new items, because the index N represents that we consider that new items, and in the forward logistic, and in the reverse logistic, we consider the used good, so they are not a new item. So we consider in this case the management cost, or for example, we consider the social network advertisement function and the other function that we can see in this table are, for example, the selling price of the new product. In this case, now we consider, so we pass to the consumers. So we consider the optimal behavior of the consumers. As I said before, we divide the consumers into different supply chain. Like we consider the forward supply chain in which consumers purchase new products. And in the reverse supply chains, consumers act as a collector and sell their goods on the platform. And these items are purchased by consumers at the demand market. In fact, in this work, we consider a closed loop supply chain network. And these are the consumers in the consumers logistic equilibrium condition for consumers at demand market K. I remind that with R we indicate the retailers, and with K we indicate the consumers, and these are the variables that are in this stage. And for example, we consider the product shipment of N between R and K, that is indicated by XR, K, and T, because it depends on time, and the transportation cost for N purchased from her, or the demand of new item at the demand market K. And also we consider the sale price associated with a new item N. This is the consumer in the reverse logistic. So in this case, we consider KC, that the capital one, so the capital KC represent a subset of K, of the consumers. And KC seeks to maximize his profit using the maximization of that function that we can find in this line, subject to these following constraints. And also in this case, we can consider the consumers and the collector. The consumer is indicated by K and the collector by KC. We consider the product shipment of U between KC and K using the platform, the online platform. We consider the product shipment of N between R and KC. Also, the maintenance and restoring cost of the collector, the transporting cost, the price that is charged by the collector, the portion indicated by mu KC that belong to the set 01. And this portion of view that KC decide to sell on the platform. And also we consider the amount of items in the collection of collector KC that is indicated by capital Q. And finally, we have to consider the platform gets a percentage of sale price that we indicate with gamma. In the reverse logistic, also as the forward logistic, we have equilibrium condition for consumers of the 1K. And in this case, we consider these equilibrium condition. For example, we indicate with the row star the willingness to pay the second-hand items at the demand market K. So if there is a shipment between KC and keys, so between the collector and the consumers, then the total cost is equal to the willingness to pay of the demand market K. Or for example, that if a new item is sold, so you can find a new item, the price of the used product is higher than the new one, because in this work we consider rare collectibles. And finally, briefly, I consider the equilibrium condition. And so we have to consider, for example, for the consumer condition, the following constraint and the following subset that we indicate with SK, that is not empty, convex, closed, and bounded set. And we solve our model using variational inequality. This is the variational inequality of the consumer conditions, but we solve the problem for all stages, and finally we solve the unified evolutionary variational inequality. And finally, this is the mirror of the online platform. And also the platform want to maximize its profit function. So in this function, we have to consider the management cost of second-hand product that has the platforms. Or for example, the percentage that the sale platform has, or the total amount of items due on the online platform. Or also the risk aversion function, because sometimes some collectors or reseller on some online platform like eBay are trust or not trust. So it's important to have a risk aversion function, or also a transaction cost function. And I remind that the consumer is indicated by K and the collector is indicated by KC, and the upper index U represent the second-hand item. These are the equilibrium condition. As I said before, we consider the closed loop supply chain network, and is at equilibrium if the forward and then the reverse flows between the tires of the decision maker coincide, and the product flows and the prices satisfy the sum of optimal condition in the equation presented before. And these are the theorems that establish the unified equilibrium and evolutionary variational inequality. So the equilibrium condition governing the CLC network model with competition are equivalent to solve a single evolutionary variational inequality for all the problem. And so the equilibrium condition governing the CLC network model with competition are equivalent to the solution of the evolutionary variational inequality given by the sum for all manufacturers, all retailers, or consumers, and the online platform. This is briefly a numerical example. In this example, we consider two different manufacturers, two different retailers, two different consumers, and finally a consumer became a collector, and we indicate by KC equal 5. In this example, we focus only for one type of item, so we consider n equal 1 and u equal 1. These are the plots that are corresponding to the results of our example. These are the solution that we find for the first behavior for the manufacturers. We indicate by the same retailer, the same color, and for the same manufacturer, the same dash. These are the profit of manufacturers, and these are the solution of the dynamic solution of the retailers. And in this case, we consider with the same color, the same retailers, and with the same dash, the same consumers that buy from the retailers. And when we see that, for example, in the profit function of the retailer, we see this upper, this maximum value at time 2 that correspond to day number 2 of a week, represent when a product come on the stores or in the shops, and this is a maximum value. Then there is a decrease of this function of the retailers, and finally there is a stabilization because the consumers has a loyalty to the retailers, and so decide to buy from these retailers that product for all weeks. And finally, this is the plot for the consumers. In fact, the solution for the last part that is indicated by X56, so for consumer number 5 and collector number 6, converts to 1, and this represent that collectors sell only 1 item in a week. And also we notice that the red line is higher than the others one, because the red one indicates the new product, the used good and not the new product. Because in our example, we study rare items that has a high price when it's sell on the platform, on the online platform. So briefly, to sum up the presentation, in this model I present an equilibrium model of a closed loop supply chain network in which consider manufacturer, retailers, the market, and one online platform in which the consumers could choose the new product and collect them. And the collectors sell the goods to consumers through an online platform that we consider eBay for our case. And we can consider, for example, that for future research, we can introduce a random factor in the demand function. So thank you for your attention. These are some related literature. This is our work that is published, and this is not time dependent, but the new one is under submission. So thank you again.
Thank you, Georgia. Very interesting topic. So we will hear from Zümbül next.
Okay.
And okay.
Good morning, everyone. First of all, I would like to thank Professor Sibel Salman for her kind invitation. I would like to congratulate the speakers for their excellent research and inspiring presentations. It is wonderful to see how female researchers excel in academia. It is also wonderful to see many familiar names among the participants. So my aim today is to provide my own overview of the current supply chain challenges and how we as researchers can help with overcoming them. Next slide, please. But before that, I would like to briefly introduce myself. I'm an associate professor at Eindhoven University of Technology, Department of Industrial Engineering and Innovation Sciences. I received my bachelor degree from Middle East Technical University, my master's degree from Bilkent University, both in Turkey. I have a PhD degree from Lehigh University in US. I joined the Eindhoven University of Technology in 2010. Immediately after obtaining my PhD degree, and I have been working here for almost 12 years now. just to give you an idea about what I do besides teaching, doing research and supervising PhD and master students, I'm the research director of the European Supply Chain Forum. This forum has more than 70 company members, and I am engaged, of course, together with a big team of researchers in understanding the real world problems and providing practical solutions for our company members. I'm leading the supply chain management team of our department. I'm developing roadmaps on how to continue with our research on logistics. I am the chair of the education committee of our department, and I'm also the department editor for our Spectrum Journal's supply chain management department. In addition, I'm a board member of the Beta Research School. Some of you might know this school. It's a school that consists of more than 10 universities in Europe. I'm also chairing the supply chain management special interest group of the AMSOM Society. And finally, I'm also the chair of the Netherlands Operations Management and Logistics Society. Next slide, please. And of course, I try to do research. I do research in a field that was very popular many years ago, and also gained significant popularity again in the last 2 to 3 years. And that is the field of supply chain management. Never has the issue of supply chain management been so prominent. So what are the reasons or events that made this field popular again? I think all of you know the obvious reason, that is the COVID pandemic. From its onset, the coronavirus pandemic caused many major disruptions to supply chains, and this led to nationwide shortages for many essential products. For example, we consumers witnessed empty shelves when shopping for items like toilet paper. So what caused the breakdown, and what can we expect from supply chains in the future? We all know that the supply chain leaders strive to be efficient, right? So their job is to satisfy customers at a low cost. And before the COVID pandemic, the focus was on lean, low cost and efficiency. Companies would develop forecasts and models to help predict demand for products, and then closer the forecasts were, the better the job of satisfying the customers and keeping profit margins growing. But with the disruptions brought on by the coronavirus, the forecasts and the predictions and the networks and all the relationships formed to deliver with low inventories were blown up. So what did we learn from the companies that successfully managed to survive the pandemic? So we have learned that digital transformation of supply chains cannot wait anymore. It was optional for some, or considered to be too hard or expensive to make the investments in people and technology while managing the risk. But now, the urgency of changing business models and supply chains to match our form of a survival. So firms that wait or refuse to change may find themselves in as victims of this unfortunate event. So the second reason for increasing popularity of supply chain management is Brexit. Brexit has many negative impacts on industry due to the new customer regulations, actually in both directions. Both the paperwork and tariffs increase the cost and reduce profitability for many companies. But even worse than the cost is the lost time. We know that the modern supply chains are often very tight. Obviously, freshly cut flowers won't do well if they spend an extra day in a truck. But non-perishable products are also often part of just-in-time supply lines. and a delay can lead to expensive stop of a plant. Industry can, if necessary, factor the delay into their supply chains. This is what we do actually in our research. So we account for positive lead times, but fluctuations of delay also increase with Brexit. Sometimes it will work well, but sometimes someone forgets a check mark on a customs form, resulting in an extra day or two until the paperwork is somehow sorted out. So this makes any kind of just-in-time delivery actually impossible. And at least currently, worst of all is the uncertainty. So will customs work? Will my supplier survive? Is it still economical to ship across the channel? So the trading between the European Union and the Britain has a lot of uncertainty. And as you all know, uncertainty hurts supply chains. Another obvious reason that impacts the supply chain is the Russia-Ukraine war. Among the most pressing problem is, of course, the over-reliance in Europe on natural gas and the crude oil from Russia, and also the dependence on both Russia and Ukraine for key agricultural commodities. Russia and Ukraine account for more than 25% of the world's trade in wheat, and also more than 60% of the global sunflower oil, and 30% of the global barley exports. Russia is also a very major global exporter of fertilizer, which means that any supply shortages or restricted access could impact the crop yields globally. It is not just oil or agricultural commodities that are under stress. Russia is also a very major exporter of some of the world's most important commodities. So next slide, please. So these are major events that brought many different problems that urge us, the researchers in supply chain management, to study new and very relevant problems. One important issue is that is relevant is the shortage of truck drivers. It is estimated that more than 70% of all freight moves by trucks. Actually, analysts and industry groups have warned of truck driver shortages for years, but supply chain disruptions during the pandemic and increase in demand in places like the US have made this slow rolling crisis much more important. The truck drivers have gone into construction as the real estate market is hot now. They went to manufacturing, warehousing, and fulfillment centers, and they picked up a new trade. And now supply chains experience very long lead times, and those are longer than usual. And the supply chains suffer from this shortage of truck drivers. Another problem that especially the coronavirus pandemic has brought up is in the chip shortage. So global-wide shutdowns caused production to freeze and the stock to drain. On the other hand, the demand for electronics boomed. We all needed new laptops, printers, and so on. And this increase in demand increased the competition between the tech giants and the automakers for chips. Chip makers are responding to the sustained demand by increasing the capacity, but it takes time because semiconductor factories cost billions of dollars to build. The bottom line is the pandemic accelerated an already risky situation for chip makers, and we are in the middle of a tech boom. Supply cannot keep up, and it won't get sorted out overnight. It means that we, consumers, will experience delays and also disappointment to months to come. The shortage of truck drivers is a logistic problem, while the shortage of chips is a supply problem. There is also another challenge that retailers face, and this challenge is generated by us consumers. The pandemic has accelerated the shift towards a more digital world and triggered changes in online shopping behavior. And this is likely to have lasting impact. This shift that we as consumers prefer online channels more than ever resulted in many problems related to last mile delivery and product returns, both of which actually already suffer from truck driver shortages. So the problems are kind of interrelated. The next slide, please. So the question now is what challenges supply chains face in a year ahead. So what can we expect? It is predicted that the disruptions are likely to follow in 2023. We are also likely to see the impact of Russian-Ukraine war in years to come. The only certainty for supply chains in the future is more disruptions. The truth is that the supply chain disruptions, shortages, shipping delays, and unfortunately price increases can come at any time. Next slide, please. So how can we researchers help with these challenges? How do I contribute to the understanding of the current problems and potential solutions? Naturally, more research is needed to understand how to move from lean supply chains to supply chains with built-in resilience. Based on my own research, I know that the companies should work on recovery strategies rather than prevention. But it is still an open question which mitigation strategies help different supply chain layers. Some mitigation strategies might help manufacturers. Some other might help logistics company providers, or companies that provide the transportation. Some other mitigation strategies work for retailers, but not for manufacturers. As I already pointed out, the customers buy more online than ever. It is important for online retailers or omni-channel retailers to manage their customer expectations with an important objective of minimizing the returns. Optimized return management policies can also help with partially solving the last mile delivery problems stemming from the truck driver shortages. Last but not least, the environmental impact of logistics and supply chain activities is beginning to be more widely understood. I'm also happy to see that our last speaker had a presentation on closed loop supply chains. If countries around the world are to meet their emission targets and commitments, it is likely that we will move towards more sustainable supply chain practices. But it is of extreme importance to transform the current linear supply chains to circular supply chains, where products are remanufactured, recycled, reused, refurbished. I'm currently supervising 7 PhD students who work on these 3 topics. So on building disruption mitigation strategies for big supply chains, on omni-channel retailing with problems on returns and coordination of different players in the supply chain, and also on developing strategies to move the linear supply chains toward being more circular. I would be very happy to discuss the details with you in case you are interested. Thank you very much for your attention.
Thank you, Zümbül, for this excellent talk. You pointed out the important challenges in supply chain management today and in the future. That was very interesting, and thanks for accepting our invitation to be here.
Okay.
So let me share my slides again. All right, we have some more thanks for this webinar support as well. And now is the time for coffee break. But before that, sorry, do you have any questions to our speakers?